Hello, and welcome to A Scientific Good Night. I'm your host Nathan Candace, and tonight we will be reading from Vector Calculus, 5th edition, for our bedtime story. Let's begin, shall we? Chapter 2.2, Limits and Continuity. This section develops the concepts of open sets, limits, and continuity. Open sets are needed to understand limits, and limits are in turn needed to understand continuity and differentiability. As in elementary calculus, it is not necessarily to completely master the limit concept in order to work problems in differentiation. For this reason, instructors may treat the following material with a varying degree of rigor. The student should consult with the instructor about the depth of understanding required. Open sets. We begin formulating the concept of an open set by defining an open disk. Let x naught be an element of r to the n, and let r be a positive real number. The open disk, or open ball, of radius r and center x naught is defined to be the set of all points x such that x minus x naught is less than r. The set is denoted d of r x naught, and the set of points x in r to the n whose distance from x naught is less than r. Notice that we include only those x for which strict inequality holds. The disk dr x naught is illustrated in figure 2.2.1 for n equals 1, 2, 3. In the case n equals 1 and x naught is an element of r, the open disk d of r x naught is the open interval x naught minus r, x naught plus r, which consists of numbers x element of r strictly between r naught minus r and x naught plus r. For the case n equals 2, x naught is an element of r squared dr x naught is the inside of the disk of radius r centered at x naught. For the case n equals 3, x naught element of r cubed dr x naught is part strictly inside of the ball of radius r centered at x naught. Definition: open sets. U r to the n, that is, let u be a subset of r to the n. We call u an open set for every point x naught, and u there exists some r greater than 0 such that dr x naught is contained within u. Symbolically, we write dr x naught is a subset of u. See figure 2.2.2. The number r greater than 0 can depend on points x naught, and generally, r will shrink as x naught gets closer to the edge of u. Intuitively speaking, the set u is open when the boundary points of u do not lie in u. The figure 2.2.2, the dashed line is not included in u. We established the convention that empty set naught, the set consisting of no elements, is open. We have defined an open disk and an open set. From our choice of terms, it would seem that open disk should also be an open set. A little thought shows that this fact requires some proof. The following theorem does just this. Theorem 1. For each x naught as an element of r to the n and r greater than 0, dr x naught is an open set. Proof. Let x be an element of dr x naught. That is, let x minus x naught be less than r. According to the definition of an open set, we must find s is greater than 0 such that ds x is a subset of dr x naught. Referring to figure 2.2.3, we see that s equals r minus x naught is a reasonable choice. Note that s greater than 0 but that s becomes smaller if x is near the edge of drx naught. To prove that dsx is a subset of drx naught, let y be an element of dsx. That is, let y minus x be less than s. We want to prove that y is an element of drx naught as well. Proving this, in view of the definition of a R disk, entails showing that y minus x naught is less than r. This is done by using the triangle inequality for r to the n. Y minus x naught is equal to y minus x plus x minus x naught is less than or equal to y minus x plus x minus x naught is less than s plus x minus x naught is equal to r. Hence, y minus x naught is less than r. Example 1. Prove that a is equal to x comma y as an element of r squared. X greater than 0 is an open set. Solution. The set is pictured in figure 2.2.4. Intuitively, this set is open because no points on the boundary, x equals 0, are contained in the set. Such an argument will often suffice, for one becomes accustomed to the concept of openness. At first, however, we should give details. To prove that A is open, we show that for every point x comma y as an element of A, there exists r greater than 0, such that d of r x y is a subset of A. If x comma y is an element of A, then x greater than 0. Choose r equals x. If x1 comma y1 is an element of d of r xy, we have the absolute value of x1 minus x is equal to the square root of x1 minus x squared is less than or equal to the square root of x1 minus x squared plus y1 minus y squared is less than r is equal to x. And so, x1 minus x is less than x, and x minus x1 is less than x. The latter inequality implies that x1 is greater than 0. That is, x1 comma y1 is a subset of A. Hence, d of r xy A. And therefore, A is open. See figure 2.2.5. It is useful to have a special name for an open set containing a given point x, because this idea arises often in the study of limits and continuity. Thus, by neighborhood of x as an element of r to the n, we merely mean an open set U containing the point x. For example, d of r x naught is a neighborhood of x naught for any r greater than 0. This set A, in example 1, is a neighborhood of the points x naught equals 3 comma minus 10. That concludes our reading for this evening. I hope you had enjoyed this edition of A Scientific Good Night, and may you sleep well.